Welcome all. Welcome to the EasyPower Thursday webinar series, where we try to present perspectives from different points of view on electrical system design, analysis, and safety. And today is no exception. My name is Jim Chastain. I'm an applications with engineer, and I'm the host for today's session. Before we introduce our guest speaker, as I'm in the habit of doing, I'd like to conduct a couple poll questions just to get some feedback from the audience as we get started. So again, thank you all for attending. And here's kind of what we have in mind as far as poll questions. And if you would please help us out by participating with your responses. Obviously, there's no obligation or liability, but it does help our presenter focus the discussion and understand perspectives that people may be coming from. We try to maintain a fairly informal format for these sessions, and we will have a Q&A session at the tail end, but by all means, as questions come up, feel free to enter them on the question box on the control box. So it looks like we have a quorum here. Thank you. So here's how people have weighed in on this. It looks like we have a pretty good mix of participation. And our second question is how you describe your primary function in the world, at least in the corporate world. I know we've had a lot of registered attendees for this session. It's a fairly popular topic, and I think we're going to have some good dialogue as we go through. All right, here's how people have weighed in on this question. Pretty much our typical audience. And then finally, how often do you have these kind of issues? And obviously, if you're a consultant, it may be something that you run into more frequently than a facility person, but we give you a chance to kind of chime in. And judging by the attendance, there could be a wide range of responses here. Okay, good. Let's share how people have voted in on this, weighed in on this. All right. At this time, I'd like to introduce our guest speaker. Mark is the Vice President and Technical Director of DEHN USA, and they focus on solutions for lightning and surge-related problems in the North American market. We are pleased to welcome as our guest speaker this morning, Mr. Mark Hendricks.
Thanks, Jim. I'm really pleased to join your team and join this exciting webinar series. I think it really helps bring the solutions to the market space. And what I really appreciated the audience's participation to answer Jim's polling questions. It's really helpful to see just a snapshot of the types of industries and the types of players that we've got. Okay, so just a quick, by way of introduction, picture of myself. You can see I've got a face for radio. Thanks for the opportunity to keep it informal here. So the topic that we really want to cover is national fire protection, and it has many reaching pieces to the codes, to how the NFPA and how the IEC methods harmonize. And what's really a great opportunity for us today is talk about how the surge protection, what we consider the surge protection portion, is essential in the overall. That's what we're doing, and we're keeping it, focused on the lightning protection side. And the national electric codes have some pretty clear guidelines on where you have to mandatory as opposed to suggested informative. So the normative requirements fall into human safety areas where you've got industrial machine interlocks, and it also has applied to dwelling switchboards, breaker panels. You see it mandated in the wind generation industries because of the risk of fire, direct strike lightning on these generators is a big deal. Emergency systems, in fact, all your e-lighting, exit sign type power panels all have to have SPD installed on them to protect those systems critically. And then the operations power systems at first responders, homeland security, federal broadcast, the emergency services, hospitals, fire and ambulance services all sit on a communications backbone that all have mandatory SPD requirements. So that's the type of things that have to have surge protection. But you'll see in industry that you'll want surge protection because of the environment. And so we've got a couple of quick descriptions of what the threat environment looks like. So direct strike, of course, that's the big kahuna, as it were, where the charge moves through the atmosphere. It strikes from 10 miles away, moves horizontally, moves sideways, vertically, and it attaches, and you have the discharge event. That's the full lightning strike effect. And that is, of course, very energetic, and there's lots of descriptions in the standards that tell you, how much current, where does the current go, what should you expect to see. That's in relation to an indirect strike where you got struck, but it's the building next to you, so you only indirectly experience the ground potential rise, or only there's plenty of it, but only the electromagnetic effect where it's coupling into the wire. It doesn't have to strike the wire for it to still induce surges. And it can come from far away, and those are considered indirect, but there's still lots of energy in what you would call an indirect strike. What's nice about this illustration to the upper right is that it shows the main discharge event, but it also shows what's happening due to the electric field of the charge. Momentarily, it moves through the atmosphere, it stops for an instant, provokes a huge electric field. That electric field is drawing step leaders from everything in its influence in a spherical sort of world. And the closer you are, the stronger the effects, but there's still in all three dimensions around it trying to attach and be the lucky one that wins the lightning. And that's a really nice photograph that we've got from, this was first seen in National Geographic, but it's a sycamore tree versus lightning. And it tells you not to stand under the sycamore tree during the lightning event. But you'll notice it has photographs, evidence of the step leader attachments trying to win. And here you see it hit an antenna into the house. It blew up the electronics of the house without being necessarily the direct strike. But you can see that those step leaders are trying to attach. And that is part of what's considered the lightning protection approach, is that you need to understand how lightning is likely to attach, and then we take the measures to protect against it. And that's the discussion today, is focusing in on one of the things you have to do for lightning protection. And it is the surge protection and bonding. And that's why the polling question was really about this portion of the principles of lightning. And allow me, the air termination system, Ben Franklin introduced this in 1753 and immediately put it out in public domain in the Farmer's Almanac and described how to do an air termination, a down conductor, and an earth termination rod, like an earthing rod, and described them suitable to serve as the external lightning protection of the day. It saves countless lives from fire. And what wasn't as abundant, and certainly not understood at the time, was that you need to make sure to separate your lightning from your other electrical devices. Now, 1753, there wasn't many. Now there's lots. And so these two that people pay the least attention to are actually incredibly important for us in our modern world, where You have separation to the rest of the things around you, like the oxygen in the hospital or the gasoline lines at a filling station. You don't want it to strike that. So that's separation. And then finally, we want to talk today about lightning equipotential bonding portion of the overall, the world. Okay, so that is essentially bonding metal to your bus bar. Bond that stuff. That is the number one thing you can do to help your systems, is to have a clean master ground bar and direct lines. Everything's connected directly to the master bar. The master bar directs directly to the earthing system, short, straight leads, big gauge conductors, clean connections. And so in this diagram, we're seeing the bond to the earth electrode. It can be a ring, it can be stuff, you know, the interconnected vertical rods. The lightning conductor coming down the side of the building, okay, that's the down conductor portion of this earthing connection. Notice it's separate from your works. You don't want that lightning into this gas pipe, separate from and its own dedicated connection. And pipe and metal works, of course, that's directly bonded. Surge protection serves that purpose for your electrical connections. If you can't bond it, equipotential bond it, you have to equipotential surge protect it. And that's what's happening with your other lines. Your data and your power lines are being protected to that master bar. So it's essentially equipotential bonding for electronics. So what is it doing? It sits there transparently and allows your power and your data to operate in a normal, clean, blue sky day. So that's the day your electrical system gets installed. It's brand spanking new and it has no deterioration. Nothing's ever gone wrong. But over time, you get lots and lots of lightning, and those voltage surges induce stresses electrically into your systems. So what we're doing is we're controlling that voltage to some predetermined level, and everything above it, it chops off or diverts. So that the most important things lots of things are important. The key things to look for right away is, what's the operating voltage, maximum continuous operating voltage of your circuit? If it's AC power, fine. If it's 4 to 20 milliamps, we know that's 24. Boom, we can just march down, talk about the voltage. Then it's the VPL. What does it really control that to? If it's really sensitive 5-volt circuit, you want a really sensitive VPL. And then the other big term you see is the surge current. You're going to divert away from the victim. And that's essentially the current that is in this top spike is what you're diverting away. Many descriptions of it in the technical standards. It's rated in microseconds, milliseconds. You have all sorts of different descriptions of it, but it's generally seen as Ka in microseconds. That's the market we're talking about. A surge protector is not the same as a high voltage arrestor out at 100 kV line. Those products exist and they're important. Those are arresters. Surge protection is described as below 1,000 volts, 1,500 volts for DC photovoltaic. Okay, so we want to chop that bit off the top. So what's the surge look like? Well, it's coming down, and one description comes down the down conductor and induces voltage, and half of the current diverts into the earth and the rest actually induces into the rest of your building. So this is how it's described in the standards, that when you get struck, you can expect something to happen, and that's that voltage rising around your system. And then when this surge protection is trying to operate, you can actually have follow currents and things as well, and these are all part of the surge world. But this is essentially the short description of what's being induced into your systems. And this is just a quick photograph of the image off the oscilloscope. This is what you're doing. You're chopping the spike off and allowing the AC power to have operated transparently. And you're inducing the surge into the return. Essentially, you're diverting the surge. Okay, so the types of systems we're looking at. Where will NEC tell you to look? It'll advise you over your power over Ethernet. This is a really important aspect with the security camera systems, with card reader access systems, radio frequency antenna surge, coax lines for television and old-fashioned cable and old-fashioned radio, the high-speed 5G applications. These are all part of the radio antenna world. Low voltage control for variable speed drives, flow meters. Of course, this is ubiquitous across any of the process control world. Emergency lighting panels. This is an area where it's mandated to have SPDs. Safety intrusion alarms on that high voltage. For instance, your high voltage MCC cabinets will have, the access doors will have little intrusion safety switches. Those safety interlocks have to have SPDs to meet the code requirements. OSHA and the NEC and NFPA code requirements, they look very carefully at that circuit. And then just standard 122.08, 277.480, I call it just standard distribution. These are the applications which are ubiquitous through the process control. What does the surge protection doing? It's preventing the voltage from sparking across what should have been bonded. So you can't bond your electrical power, but you control the voltage. When the voltage gets out of control, it gets out of the wire. And this is destroyed service entrance boxes. This is destroyed power wall outlet and data line coupling circuits. This is destroyed telephone, started a fire. You have lots of examples from your own world where you actually can't even find what burned out, but your printer's dead, and it happened during the lightning storm. So you know it burned something out, and now you get to go troubleshoot and replace your equipment. It can be very obvious. Here we see transformers on fire, and here you can see vast damage from one of the cables. Might have had a problem, but the result damage to all that I/O wiring. You see very obvious transformer damage on small power supplies. You can imagine what it's doing to a microprocessor power supply. You can see the damage. It blows the jacks off of these RJ45 type power over the Ethernet circuits. You can see it actually cause a small burst in the earthing and shielding on a cable. When there's enough surge, it'll blow the jack off. When there isn't enough surge, it will essentially be absorbed into the rest of the equipment, and so those stresses are happening to your cabling, and over time or through one event, you can see that you can actually have the jacket burst and arc into the shielding, arc into the actual data cables. So there's a lot of damage that can be incurred that you don't even see because it's buried within the rest of the system, and it's not brand new anymore. And so this is something almost like lightning fatigue into an electrical system. So you can see the results with jacks being blown apart, but you don't necessarily see it in all those hidden cables. So when we have an opportunity to examine at the sort of top down, what's your line diagram look like? We'll take a look at things like solar industry, which is an optional industry for surge protection, but if your operators in this industry want to keep running, they're going to pay a lot of attention to the surge protection devices on the power lines, DC and AC power lines, the DC control lines, the IO lines that go back to the mains and the master control inverters, where you're watching what's going on in the panels. And so when panels start going bad, you have excessive currents and voltages because it's trying to keep up with the rest of the panels, and it's trying to regulate its voltage, and it causes stresses in all of the collection systems. You also want to watch for the data lines. You don't want a back door left open into your master control center from a power over Ethernet camera that was at the fence. And is it directly incoming inline back into your router in your switch room? with all your other security camera requirements, and that camera is now compromised. What does it look like at a more complicated load center? You'll have your mains inputs, you'll have the expectation to put a larger surge protection at the front of the building where you have that likelihood of the ground potential rise, and then you have a smaller SPD coordinated with it at downstream from it after you enter the distribution system. Perhaps it's on the downstream side of the backup generator. So you'll have, absolutely mandatory things like sump pumps on job sites that have their own backup generator, so that during the lightning storm, the surge of the rain is also causing you issues in your drainage systems. You don't want to lose your sump pumps in these emergency situations due from flooding and lightning. So you'll often see these transfer switch applications, and we recommend to coordinate and put surge protection on the downstream side of what is clearly an emergency service application. So we talked real quickly about the types of systems. This is what it looks like when it's installed correctly. This is what we're looking for. When you get to a site, and in this case, it's a public audio address amplifier that is required from the nuclear regulatory industry around our nuclear sites that have any operating or storage lifetime. And there are, some of these 5.9s industries that require operation through every event. So when they are doing a public announcement, this speaker will work correctly, this audio amplifier and speaker set. So what are we looking for? It should be positioned near the point of use where it will make a difference and control the voltage at the amplifier. You want to use short connection wires. You want to avoid tight bend radius. You want to use the heaviest gauge possible. You want to direct connect to the earthing bar, which you can see we've easily and effectively set up with this surge protection arrangement. And in this case, it has gain protection for the DC output of the red and the black, but it also has protection of the rest of the CAN bus and IO control within a cabinet like this. So what does this look like with industrial control and process control? You want equipment to have its own dedicated bond back to a master ground bar. You want the valves to have lightning protection and be properly grounded. For cathodic control systems, they're floating. So you need to make sure you're watching what's grounded, what's not grounded. But what's important is that they have dedicated runs back to the single point master ground bar. The SPDs are as close as possible next to the variable speed drives. Proper control of the shielding. It's usually lifted at what's considered the control cabinet, but that's a big discussion of its own. Good earth connection systems to the actual master ground bar, and good bond connections on the equipment where the pumps and the valves have obvious and secure bonds. And then where does it look? Where does it appear? Where does a surge protection need to go when you're between a variable speed drive and a motor? Do you want it next to the motor? Do you need it next to the output of the inverter? And so there's also discussions about the length of these cables. Are they greater than 10 meters where you see that you'll need protection on both ends of these devices? Here's a nice cabinet, but in all of its nice workmanship and good clean arrangement, what is not obvious is that there's no SPDs on the AC power protection. There's no SPDs on the low voltage data signal applications. There's missing a bond on the front door. Now that sounds subtle and like, well, that's no big deal. That stuff is a contributor to other noise issues. And you'll see other examples where we can show that dead front should be dedicated bonded. Whenever you see a cabinet that's got something like a light on the outside of it, a control dial, well, that's an opportunity for it to be arcing to the door, and you must have that bond present for that safety, for that electrical apparatus. We see a lot of vibration control systems, motor flow meter control systems, and what's important, of course, is to have the SPDs on the power, but also on the data line that's often next to the motor control system, monitoring and doing its Profibus or whatever the CAN bus type circuits. What's really important is to pay attention to the 4 to 20 milliamp control cabinets and make sure that you've paid attention to that shield and you watch for distances greater than 10 meters where you'll know you'll want protection. What's interesting about some of these applications is that they're mounted on steel pedestals, but the steel isn't bonded to anything. So essentially this looks earth, but it's not earth. It's literally floating over this water control panel. So that's really important to pay attention to how the ground wire was mounted and installed on these types of applications. So you're avoiding weird ground loops or secondary loops. Safety interlock systems. This is one of the areas that are mandated by the standards. So it's an important aspect of that you can bring into your maintenance plans, into your inspection systems, where you're monitoring your intrusion alarm and you're making sure that the system is properly surge protected as part of its maintenance cycle. So these are the things we check the system for. SPDs on the low voltage, proper treatment of the shield, close as possible to point of use, good bonding systems, good cabinet earthing systems installed where you can clearly see the bonding conductors. Flow meters, this is a nice photograph showing the actual surge protection device installed at the flow meter point of use, properly dealing with the shield and the grounding wire systems with solid connections back to earthing bus bar control. What does it look like at a dwelling? So you can have any number of complicated load centers. The idea is that you want to have the surge protection as close as possible to the main bus to do the most good for the dwelling. So in this case, what you're looking for is to have the surge protection directly on the AC power feed. You want to make sure you're paying attention to the ratings of the devices so that you can advise if they need fuses for disconnects, or very often our products do not need fuses to be installed on such load centers. You want short connection wires, you want a direct connection to the earthing system. You also want to pay attention, some manufacturers include surge protection with their panel. If the event of that has something that looks like the catastrophic failures we saw early on in our photographs, you want to consider having the surge protection device next to, but not inside of the same panel. That's preferenced by the application. We talked about requirements in the wind power industry, and we have a good combination of excellent wind energy applications here in the US and lots of lightning. And so this is a combination for the service industry that needs to go up and maintain these devices. There's any number of damage in the mechanical rotor systems that can be controlled with lightning protection and surge protection. So it's important in this industry, which has such high maintenance costs, tower climb, road access, and you know, of course, weather delays to go do any of this work. You can see that this is a really high importance to have addressed all of the applications up at within these inverters, where you're looking at all of the direct inverters and all of the IO controllers on these types of applications. Emergency systems. Well, this one it's easy to understand that you have to have exit from your building in the case of fire. So this is a clear, easy place to make sure that is taken care of first, and same applications apply for the product near the point of use and short connection, direct connection to earth. So control rooms at first responders, control rooms in your IO factories, in your process industry, wastewater, power generation. Everybody has something that looks probably similar, where you've got the SPDs at your load center. You need it on the actual far side at the measurement control systems on the cameras, at all of your maybe card reader access points. You have SPD on the physical coaxial radio control systems. You have SPDs on your power over Ethernet related I/O circuits. You have clean grounding bars. These are the things that we're looking for to make sure that it's a good sign of best practice installation. First responder security camera systems, and this is, of course, the cameras are going to pretty soon outnumber citizens, but you can see that the camera has an outdoor portion of the apparatus that needs to be protected at the actual camera end, and as importantly, or more importantly, is at the indoor end of the power over Ethernet circuit, where it needs to be applied on the router input before you get through the device. So these are considered series devices, where that protects the circuit in series with the operation. And again, it's important to protect at the point of use, both ends at the outdoor, sorry about spelling mistake, and grounding and bonding and protection. They go together as part of that overall lightning protection. What you're looking for is to make sure that the SPDs are installed correctly to the manufacturer's suggested operations. You make sure that you pay attention to shield lifting on your data circuits. You want to make sure that you have that good door earthing bond. And there's plenty of applications where you'll get a chance to see this bond correctly installed. You'll be looking for the similar master bar inside of your cabinet. You're looking for single point of earth, something that you hear the term star bond. But what's important is that you're looking for a good solid earthing system to supplement and take care of the electrical operation. So some hints about selecting SPDs. Of course, the manufacturer's websites are all a little bit different. There's several things to look for to make sure that you're picking your device the proper way. You're looking for your AC voltage. You're looking for the configuration. Is it something like 12208, 12240 split phase? What's the system that you're looking at? What is the SCCCR, the short circuit current rating of the AC power system? Remember, the SPD has to match what your system short circuit rating is. So if you have a breaker upstream feeding your motor control center, you look at that breaker, it'll tell you it has a short circuit current rating, probably 200 kA, that's highest sort of accepted rating. The SPD needs to match that rating or be disconnected from that breaker. So it's a really important aspect to match so it safely meets what the system can deliver as a fault. And then where does the SPD get installed? Does it get installed at the panel, or do you install it downstream directly off the motor or the variable speed drive? We have very helpful tools on our website where it's easy to pick out your electrical service, and it gets you to a product in just a few clicks. So it's easy to pick out the right products if you know your system voltage, which comes right off of your system transformers and panels. And it's important to understand, are you installing upstream of the breaker directly across the line without fuses because you can meet the short circuit current rating, or do you need to be installed off of fuse disconnect means, installed downstream from the fuse or your breaker panel? Data circuits are much the same way. You have an operating voltage that you do not want to go above. The idea on if you know you have a 5-volt, very low voltage controlled sensor, then you want to stay with a very low voltage protection. If you have something that looks more like a 24-volt circuit, then you pick the higher protection operating voltage. How many signal wires? 2 pair, 4, 1 pair? What does the connection means? Is it stripped wires that you terminate into like a patch panel for your phone room, or is it RJ45 connections? And then again, where does the SPD get installed? So on our data sheets, you'll see the things that are important for protecting your circuit, and diverting current away from your victim. So that wraps up the portion of our material. I'd like to open it to Jim to see if we have any direct questions that we're able to answer and attend today.
Yeah, Mark, we've got several questions. First one that came in is actually from someone who's familiar with the DEHN company. He wants to know how to protect an external RFID reader, which is mounted on an 8-foot high pole and has devices for mobile phone and security cameras.
So that sounds like something that's, it's likely it's power over Ethernet sort of apparatus up there. If it's PoE, then we've got products that literally plug in with RJ45 and you mount it right next to it on the pole. And that's a product that we can send you a link to and answer your question directly. It's actually one of the photographs of the power over Ethernet camera slide that I had. That can be any power over Ethernet apparatus. And essentially what you're doing is you're mounting it in series at the point of use and back at your control center, because that PoE is it's coming from a router, an actual network hub. So you want to protect at that rack as well. So, and that's why that picture had the both ends. I hope that's helpful for this question. We can certainly tackle that in greater detail. If it's a different type of circuit, it might have its own 24-volt power supply, and it might have a 120-volt, transformer up there. It might be more complicated. So we can look at that. That's a great application. Very, very important for restricted access and security gates. Yeah, I get that.
The next one is from Aggie Doctor. If main distribution panel has surge protection, do the downstream panels require it too, or does this just add to the cost of the project?
Well, the standards give you a 10-meter suggested, we'll call it grace range, where if you're within the same room that's substantially shielded and you're 10 meters away, you're probably not experiencing much in the way of GP, ground potential rise. And you're close enough to enjoy the benefit of that SPD. When you get farther away, you may not care that maybe it's a big pump that has a very high voltage insulation on its wires, and it's fine. It can withstand actually quite a bit of abuse, call it over voltage, without it really arcing through the wires. But if it's something that looks like a more sensitive variable speed drive, and you're out in your industrial plant, more than 10 meters, you're probably 100 meters or something that looks like a pretty good distribution run. That's where you want to consider that you want it on both ends. And that's from the standard. And then you'll sort of learn your own best practices. Other industries, Motorola, for instance, has R56, and they define in their standards how they suggest to put extra SPDs. I think there's a lot of good discussion in NFPA. It tells you in front of your transformers, behind your transformers. I think there's some good precedents.
The next question is maybe a little more philosophical, but the question is from Dean: would our world be better off if the world had never heard of isolated ground systems?
Isolated ground systems. Yeah, well, I think the world would be better off without electricity, but I'd like a hot cup of coffee in the morning. I'm not going to lie to you.
Yeah.
So the real problem is, how do you talk between an isolated system to the rest of the world? If you're through radio waves, you're fine. If you're through fiber, you're fine. If you're in the same block in the city, if you're substantially on the same, what considered a city block where the ground is all together and you don't have massive potential rise between two adjacent buildings, it may not matter as much. But as soon as you're into a communication on a plant, you want bonded systems. So that's just my philosophy. Don't leave that metal afloat. Okay.
The next question from Habib is: can the master bar be separate to different lightning down conductors?
There's a philosophy on what that should look like, where your down conductor merges with the grounding system and where the master bar merges with your electrical system. And there's one or two of my slides had a picture or sort of a diagram of what the earthing looked like. And there's the standards will tell you don't connect other stuff to your down conductor until it's in the soil. That lightning down conductor is not your friend for any other grounding or bonding purposes until you've seen it go into the soil. And after that, you can only trust it a little bit because of the 50% rule, where it's reflecting some of that energy right back into your electrical system anyway. So yeah, the more isolated that down conductor is from your rest of your master bar, the better.
That was a good answer. I got it. Let me interject a couple housekeeping notes. All the attendees to the webinar today would receive an attendance certificate that many people use to support their EAUs, and that will be released at the same time we post the copy of the video, the recording, to the website. So those of you that may have come in late, I'd encourage you to access that and pick up on any of the details that maybe we covered early on. Here's a question.
Jim, to that point,
Sure.
If I may also expound, I have the Florida Professional Engineering Certificate number for Jim, and I'll make sure he has that for the credit on your cert, as to make sure that if you need to file that with your CEs, it's eligible for 1 hour. I'm sorry, full hour today, so 1 credit hour.
Excellent. So the question from Lionel is, what is the recommended procedure of grounding the shield wire, the drained wire, etc., in low voltage applications? In other words, is it acceptable to bond at both ends or only at one end? And if it is only the one end, which end do you recommend, source or load?
So yeah, that is in fact an open end for troubleshooting right now that I've got a customer in the power industry, and we're tracking that exact issue down. Is, do you bond both ends? Almost never. In fact, when you look, you always want to see it bonded at the instrument, I'll say the far away instrument, and floating at what might be your PLC. Think of your control cabinet. It's going to look something very substantially like that. You're going to have a flow meter, you're going to have a cabinet more than 10 meters away. The field should be lifted at the control cabinet because you want to keep that the cleanest. You don't want that noise coming in. Okay, then there's the other version where everything's landed at the control cabinet and the instrument floats. I think that's harder to keep track of, to be honest, because and you're sort of opening yourself up to this big ground potential field. You've made your antenna bigger, because now ground potential rise on any end of this thing is going to come right through your control cabinet. So maybe you don't want those currents coming back into your control cabinet. This is an open discussion point that I'm going to write a blog on this topic coming up. So I look forward to maybe getting some hits on that blog when we post that. It's a really important troubleshooting issue. The good news is that you should put a surge protector on both ends. That's what's important.
All right.
That was a little plug there, Jim.
Yeah, I noticed that. Here, getting this one. If a surge protective device is installed on the main incomer breaker of a motor control center, is it required again on the downstream feeders?
So we're back to that sort of question. If it's more than 10 meters, you want to be considering it. You also want to look at what is it actually feeding. If it's feeding an emergency light panel, then yes, you have to have it right there at that E light. If it's feeding something that looks like the big halogen lights from a warehouse, they're probably not as sensitive. So it does matter what your load looks like, and it does matter if that is something that's going into a more sensitive control room. So So use a hospital, because it's really easy to tell you're at the power distribution panel or you're in the emergency operating room. You'll want to have put more SPDs. So on your scale of importance of your operation, you can decide if you want to be in that operating room. So some applications mandate it, and some leave you some leeway so that you can control. Obviously, cost control is a big deal. I get that. And so, the selection and placement of that first SPD makes a big difference to how well the system is actually protected as well.
The next question actually comes in a couple different ways. First is a request for comments on surge protection for high-rise buildings. And then the second, what type of surge protection should be used on fire protection in multi-story buildings?
Oh, really good question. Generally, what you see on floors of a building is what looks like an electrical closet on every floor. Every one of those floors has what essentially looks like a small ground system. And in a high rise like this, it is suggested at each floor to have an SPD in that panel, because think about what's coming into that panel is all the electrical feeds. If you open up a panel, you're going to see a bunch of white wires, your neutrals, a bunch of greens, and then your hots in that electrical panel. You want to have protected that local panel, because then you get a good benefit to the entire floor. But that floor acts like its own little universe. For, come on, it's of course talking to the other floors of the building, but essentially it's its own electrical panel. So then you want to pay attention to the next floor. Now you look at the building steel. What's it doing? The building steel is all interconnected as well. So the bonding system and then the electrical protection system, you create its own plane essentially on a given floor. I hope that describes part of what I'm trying to make the point.
How does that impact fire protection system?
Yeah, and fire protection would be a mandatory SPD. So you'd go to all of your, you'd have a feeder circuit, so probably something like a power supply. So you'll protect your AC power, and you'll protect all the data lines coming in off those, anything in the fire control circuit. So if it's looking at sensors or oxygen, CO2 alarms and things like that, it will have an SPD at your panel. Should have an SPD, and it might be built into some of the apparatus. It's hard to, we'd have to analyze it. I know that's a complicated answer, but there it is.
So here's one that kind of brings it back to the host of the webinar. How does surge protection devices reduce or impact arc flash in low voltage systems?
It's a really good question, because arc flash is killing somebody every day and twice on Sunday in the USA. Arc flash is very, very dangerous, and it's the people in the industry that I know, they have sort of there's easy attributable causes: housekeeping neglect, intrusion of insects, intrusion of the atmosphere, whatever, the dusty atmosphere. And these things are all related to arc flash. So then what could lightning contribute? Lightning stresses your electrical distribution system. It stresses the breakers and the fuses. So the things you're relying on to operate the most safe when you need it have been overstressed and abused, call it abused, their whole life. While they were doing their deal, they were sitting there minding their own business, but lightning was striking every day out at this wastewater plant. Those breakers are being taxed. Those contactors are not indestructible. And if they did trip throughout their life, the worst thing to try to troubleshoot that I've ever chased was a 750 amp breaker that had tripped a couple of times, and it was dead. It was dead. You got to replace the whole breaker, because, sorry, they relaxed that little magnetic sensor and it was never healthy again. Was that a lightning surge or just tripping. But that to me was evidence that it actually happens, that the system does fatigue. So if it fatigues, do you want that to have been the source of arc flash?
Well, then the follow-up question, does DEHN have arc flash protection systems that can reduce or limit short circuit limits?
Yeah, we actually have a family of detection systems that actually, it sees the flash and can tell you to open up your systems. We can interlock with your main disconnects, and it can tell you that the flash is happening faster than the current is actually rising to trip out your breakers. Mm-hmm. So there's devices that acoustically and through visual systems that monitor for flash, and it compares it to the operating voltage. So it can be as it can integrate with your entire load center MCC and be as effective as for whatever you're looking for. If you want to watch for the visual, the acoustic event, but the intent is to disrupt it before the high energies have gotten out. Yeah. Right? You want to quench it as fast as possible. We have some very effective parts that we can answer that question with.
So back on the topic of lightning, is it safer to use down conductor or use the body or the pole or mast to dissipate electrical energy during a strike?
So in the 5 pillars of protection, in that discussion, there are the questions of equipotential bonding and separation. If it's a big steel tank, you can use the structure as of the steel as the down conductor into the earthing system, and you won't have compromised the structure if it's greater than the limits in the various standards. It basically looks like about 5 millimeters, quarter inch. If you're a gas oil storage tank and you're thick enough and you're beyond the wall thickness, the structure is considered intrinsically safe because it's such thick metal, even a puncture direct strike won't burst through. Okay, that's an extreme example. You're probably a co-located building and your down conductor's going past, Gladys the neighbor, and she loses her TV every time there's lightning strike because a down conductor's flashing into her electrical system on her floor. So you've paid attention to having a down conductor, but we are missing the separation from that down conductor into the rest of the structure that matters. So that's an analysis that we can do to look at a building. How tall is it? What's the separation supposed to be? Is it justified? Is it paid for itself? If you can't, then you have to hold it away, and there's methods to isolate the down conductor from the building. But that's the other point of the standard. We want to pay attention to all pillars.
Okay, so here's one. It says for an ungrounded 480 volt delta connected service at 480 volts, 3-phase, what should the MCOV rating be?
So I heard a 480 volt ungrounded delta.
Yeah. 3-phase.
So 480 volt ungrounded delta. You want so your system is your motor and your variable speed drive are operating on a 480 volt peak to peak. So the MCOV should be above that level. So you see numbers that look like at the minimum is the square root of 2, because we know that the square root of 2 is the actual peak of the sine wave. So 480 volts looks like average power. The peak is actually square root of 2 higher. So you need to get your MCOV above that operating condition. In DEHN products, we have a very clear description of what our MCOV on 480 volts is. And I would go right to the data sheets and just specify it that way. So I don't have it memorized, I can point to it. But that's how we pick it. You want to get above the peak of the sine wave and then be out of I want to say it's a nuisance if it's too low, because even things like motor swell and things like that, stall on a motor can make it look like it's a higher voltage than it truly is.
Right. So I think this will be the last question, but I'm really curious about it, and that is, are there remote indications available to determine the deterioration of SPDs?
Yes. The data products that we have in our line have a very clever, I call it a life, that's actually how we market it, it's a life check. And it tells you two things. It tells you if it has been harmed in it, if the SPD is working, but it's felt, hey, I was hit by lightning, I'm still good, but you might want to pay attention to me. It tells you that it's been struck, and then it tells you if it's failed. And that's quite unique in the market, is that a data protector that can tell you in advance that it's coming to its end of life. And in the AC product world, it's harder to do that function because of the stress of lightning. Is it a daily occurrence, or is it something that's a couple of times a year? And if you're getting a lot of strikes, your devices can fail faster. And the life check product on the AC products is difficult to gauge correctly. So the DEHN product uses a very sure disconnect means that it's either working or it's not working. So we don't have that middle ground sensing capability. Now, there are counters available. You can actually integrate a lightning counter at your load center, and you can tell that you're getting 10 strikes or 150 strikes a year. You can use that in your maintenance cycle to gauge whether or not you should be replacing your SPDs no matter what. That's a very good question.
Yeah.
All right.
So Mark, I really appreciate your presenting today. I think it was a great presentation. I know we had a lot of interest. I just will forward the list of questions, and if we didn't hit everybody's, we can answer those with follow-up email.
Yeah, we sure will.
Thank you very much, and thanks all
Jim.
for attending. And
thanks everybody. Be safe out there.
Have a good day.